today. So first of all, okay, I would like to remind you that if you want to go for dinner on Wednesday, you should sign up here your name, so because we have to make the reservation. Just tick. Yeah, just tick. Leave a sign. Just put a tick, no, and let us know so we can make a reservation. And we have to do it by today. So yes. And okay, let's continue. Now we have the talk from Dillon Brout, right? So he will talk about the Spectroscopic Supernova Type Ia 3-year cosmology results from DES, I guess, right?
Yes.
Okay, please talk.
Thanks. Thanks, Domenico. Thanks, Rogerio, for inviting me. My name is Dillon Brout. I'm a PhD candidate at the University of Pennsylvania. I'm here. I'm really happy to present the most recent cosmology results from the Supernova program for the Dark Energy Survey. The Dark Energy Survey just had a nice collaboration meeting at Campinas, and that was 2 weeks ago now, and then I spent a week at my wife's grandparents' house in Brazil, where I struggled through some Portuguese. Unfortunately, I think my English got worse, so I apologize for that. But without further ado, I'd like to motivate why I think supernovae are super cool, how we can measure dark energy, and take you through the ingredients for cosmology, take you through our most recent results of 9 papers that we published, and then talk a little bit about the future, potentially in terms of LSST. So, many of you may know, Type Ia supernovae, we think, are dwarfs that accrete matter from some companion star. We don't have a great idea what that companion star is, but we believe that they all reach this same Chandrasekhar mass limit in which they all explode to roughly the same brightness. This is an example of one before and after, most recently in M82. And we think there are roughly 1 supernova that goes off in every galaxy per century. They're really useful because they explode to roughly the same brightness, so we can use them as standard candles. We relate the apparent magnitude, their apparent luminosity, to the intrinsic luminosity to attain a luminosity distance. And we compare the magnitudes to compute a distance modulus. For intuition here, I'm going to be talking about distance moduli and delta mu's, delta distance moduli relative to some cosmological model or relative to some other assumption of systematics. And in general, these delta mu are relatively small, and we can think of a delta mu as a percentage. So I said Type Ia supernovae are standard candles, but really they are standardizable candles. We find that we can standardize them, their peak luminosities, by the shapes of their light curves given by X1 and the colors of their light curves given by C, and we use these correlation coefficients alpha and beta to do that standardization. And after the standardization, we can get the intrinsic luminosity dispersion down to about 10%. This is what we call the roughly the intrinsic scatter. And for the purposes of today, I'm going to be focusing only on data sets that measure the redshift of the supernova or the host galaxy. There are potential future analyses that do photometric redshifts, but we're not going to talk about that today. So you're going to see sometimes I say photometric. When I say photometric, I mean photometric classification. So we will have a redshift of the host galaxy, but no redshift or any spectral information of the supernova itself. So just to clarify there. So just a reminder, 20 years ago, actually almost exactly 20 years to the day of our unblinding, Rees and Perlmutter found evidence for cosmological acceleration. This is your typical Hubble diagram. And then today I'm going to be plotting residuals to the Hubble diagram a lot. You'll notice that there's a bunch of low redshift supernovae below redshift 0.1. And then there's a bunch of high redshift supernovae above redshift 0.1. And so that's been the general way of doing supernovae analyses to date, and in our analysis as well, because it's difficult to design a survey to catch these guys that happen really quickly and catch the guys that are really far away. And of course here, it's important to have both low and high redshift because you want to constrain the deviations to the cosmological model, which happen with a lever arm at low redshift and then comparing the luminosity distances at high redshift. So the name of the game is get luminosity distances, get redshifts, and measure the effective scale of the universe over time, and then search for departures to lambda CDM. So a quick timeline of high redshift supernova surveys. So we're focusing on high redshift here. Here's the discovery. And then in the mid-2000s, you had the SNe Supernova survey, which found 70 spectroscopically classified supernovae. They didn't analyze any photometrically classified supernovae. You have the SDSS supernova survey and the SNLS supernova survey. So then in the early 2010s, you have pan-stars. And so you'll notice here, SDSS and pan-stars to date are the only surveys that have done photometrically classified analyses. And they total about 2,000 supernovae. So from the initial measurements of a few dozen, we're now up to 2,000 likely Type Ia supernovae out to redshift 1 or so. And then of course there's LSST here. So the question is, what's going on here and how are we going to make an intermediary leap to LSST? And the answer to that is the dark energy survey. So the dark energy survey construction began around 2003. It turned on in 2012 and the full survey began in 2013. And we just finished taking data. So we have an analysis of the first 3 years of data that we've just released. The dark energy survey, I'll just give a quick overview because I think there will be some other discussions here about DES. Has 4 main probes, although that has expanded a little bit at this point. But the 4 initial main probes were supernovae, weak lensing, baryonic acoustic oscillations, and clusters. The camera itself is 570 megapixels. It has a 2.2 degree diameter field of view. And it's located on the Blanco at CTIO. It's mainly a facility instrument for the community. The DES, so DCAM and the dark energy survey itself is only 30% of that time, which is about 525 nights. For the supernova survey, it has a mean cadence of 7 nights. We ensure that using a cadence monitor. Of course, for comparison, LSST will probably cut that in half. So really, we think of DES as kind of 2 separate multi-band imaging surveys. You have the full footprint survey shown in yellow, which is 5,000 square degrees in GRIZY. And then we have a repeat observation survey for supernova dedicated for transient identification in these hexes here, the blue and red hexes, which are 10 different pointings in GRIZ. And so you'll see blue, there are 8 blue hexes. Those correspond to the shallow fields, and then the deep fields in red integrate roughly an order of magnitude longer and get down to a depth of 24.5 magnitude. This is just a quick explanation of the fact that we specifically target our supernova fields to be in low extinction regions on the sky. This is, of course, a problem. We avoid significant problem, something that LSST will have to deal with, the supernova program will have to deal with, because their fields will be in all types of extinction. And we specifically avoid areas with bright stars. One thing we're really proud of is the red sensitive, fully depleted CCDs on the dark energy camera. So for comparison here, I'm showing the transmission function for SNLS, this is the Supernova Legacy Survey, which currently provides the best constraints on distance from supernovae for any rolling survey. And you'll see here in the red a significant improvement in sensitivity from DES, which is in the shaded region. Okay, so DES has discovered roughly 15,000 likely supernovae. That's not Type Ia supernovae, that's all supernovae in general, of which we think roughly 2,500 are Type Ia supernovae from our full 5-year data set. And that's using classification from 4 filters, GRIZ. But for this first analysis, sort of as a proof of concept, in order to set up our pipelines and do a concrete first step, we've decided to do an analysis of just spectroscopically classified supernovae. So we've had a program to get classifications from spectra, largely from OSDES. So more than 50% of the spectra we obtained came from the AAT in Australia. And you can see why it's a perfect match for DES. That's the field of view of OSDES with all those fibers grabbing spectra. And that's the DES field of view in the optical. Most of those spectral classifications came from identifying this silicon-2 feature in the Type Ia supernova spectrum. So here is the dark energy survey. We think we have 2,500 photometrically classified supernovae out to redshift 1.2. So that is a significant leap because all of these here is roughly 2,500 supernovae, and now we're going to double it. And we're going out to redshift 1.2. And not only are we going to double it, but we have better data quality. So the distance, so this is jumping ahead a little bit because I haven't told you how we actually get these distances, but I'm going to tell you hopefully and convince you later that we get the best distance uncertainties of any rolling supernova survey. So what this is the uncertainty on distance per supernova. In red, blue, and green dotted lines are the previous rolling surveys. And then in the solid lines are the DES shallow and deep fields. So the DES deep fields have the best constraints on distance to date. So with the best constraints on distance to date, I'll hopefully be able to convince you that we can produce a competitive measurement of the equation of state of dark energy. So what I've been talking about to this point has been specific data sets, but these data sets have then been combined into fully fledged analyses, like the joint light curve analysis, which combines Hubble high redshift supernovae, low redshift supernovae, SDSS, SNLS, and they have 740 of them, and they get an equation of state uncertainty of 0.054, roughly 5%. The state of the art today is Pantheon, which is the same data set as JLA plus the Pan-STARRS sample, and that's 1,000 supernovae, and they get a 4% measurement. And then here I put this Pan-STARRS measurement just for comparison. This is Pan-STARRS plus a low redshift sample. As I've said, you need that low redshift anchor. So just Pan-STARRS and low redshift, 400 supernovae, 6% measurement. And then DES, which we've analyzed, is just DES plus a low redshift sample, 300 supernovae, and we get a 6% measurement as well. And I'd also like to point out that we are accounting for a number of new, unforeseen systematic uncertainties. So let me try to convince you of that, and then I'll do the presentation of the results for equation of state of dark energy. So how do you get cosmological constraints from supernovae? It starts with difference imaging. We take a search image and a template image, which is coming from a number of different exposures co-added together, and we get a difference image, and that difference image will have some candidates in it. Then for those candidates, we go and get a type and a redshift. The redshift is, for the purpose of our analysis, sometimes comes from the supernova itself. We then go with our photometric pipeline, make photometric light curves. From those light curves, we standardize the supernovae into standardized luminosities, and we get a distance modulus versus redshift Hubble diagram. Of course, it's important that we need to be careful in calibrating the filters and also calibrating the distances between this low redshift sample that we use and the DES supernovae. We run lots of simulations to correct for distance biases that we might expect in our observables. We run our covariance matrix and put it into CosmoMC and combine with Planck 2015. That's what we presented as our main result. And of course, it's all blind. So we run difference imaging, we get these candidates, and a significant number of them are junk. So we go in with machine learning, and we get rid of the junk, bad subtractions, bad astrometry, whatever it is, a trail, whatever it is, it gets rid of 95% of them, and we're left with identifications that are roughly all point sources. And we also go and do real-time monitoring of the images to ensure that we have good quality. And since it's in real time, we can go back and take images if they didn't come out the way we had hoped. So we have these candidates, and then we run the photometric pipeline. So the photometric pipeline is called the scene modeling pipeline. What it essentially does is models the scene of the supernova, the environment of the supernova, the host galaxy, and then the telescope and atmosphere. And we obtain a model, and we compare that model to the data. So here's the model. It's composed of a time-dependent supernova flux, a pixelated galaxy model, and we convolve it with the measured PSF of each image of all the images in the time series. Of course, this is all done in Fourier space for speed purposes, and then we come back to real space and compare the model to the data. And we iterate with an MCMC until we get a model for the supernova and galaxy. We test our pipeline using fake sources inserted on the images. So these are fake supernovae inserted on the real images. And we go in and compare the input and fit magnitudes. And we look at it as a function of many variables. This is a function of brightness. And we find that biases are limited to less than 3 millimag. And for the purposes of our analysis, that's going to be sufficient. For example, I've included the uncertainty due to calibration in red. I'll talk about that in just a second. But it's within, it's subdominant. And when you run your pipeline, your photometric pipeline, then you get light curves. So the dots are the fluxes from the images in each band, and then the curves are the light curve fits from our light curve model. And along the way, we have a number of quality cuts to reduce our sample down to 207 Type Ia supernovae. That comes from obtaining the spectrum from the first 3 years of data. That comes from light curve coverage quality cuts. If we don't have anything past the peak of the supernova, we don't use it, for example. These sorts of things reduce our sample down to 207 supernovae. And then that's from redshifts 0.02 to 0.85. And then we combine with this low redshift sample shown in red, which is 122 low redshift supernovae below redshift 0.1 from CFA and CSP. So really quickly, the spectroscopic follow-up program that we employed was a lot of work by Christy Andrea. As I said, the majority come from AAT. You can see the scales are not the same. But there was a lot of other efforts on another number of other instruments to varying depths. And so modeling this, we have simplified as simply the efficiency of attaining the spectrum as a function of the peak brightness of the supernova. And we account for this selection effect in our simulations. Now, this selection effect, due to Poisson noise, gives us distance biases. We're more likely at higher redshift to see the brighter guys. So we model this bias, but in fact, we don't do it quite like this. This is your typical Malmquist bias. It's a one-dimensional distance bias correction. That's not what we do. This is just for demonstration purposes. What we do is 5-dimensional distance bias corrections based on simulations. So these simulations, if we're going to do 5D corrections, we need really good, accurate simulations. They're based on this package called SNe, written by Rick Kessler, who's part of DES. These simulations capture nearly every aspect of the survey and of supernova physics modeling. So we use a model for the source spectrum. We apply cosmological effects like redshifting, dimming, peculiar velocities, and so on. We apply galactic extinction, and then we integrate with the filters. But we also include, for the to make the observed fluxes appear like real DES fluxes. So we apply information about the actual survey itself. So we have a distribution of PSFs, a distribution of 0 points and noises and et cetera, that we draw from that distribution to obtain a realistic distribution of noised up supernova fluxes. And then we apply the DES supernova survey logic, which means we include the entire 5-year survey set of observations. We account for gaps in the observing program where things went wrong, and so on. And so we get, anytime we generate a simulated sample, we can get a set of Type Ia supernovae that look, in theory, just like the data set that we're observing. We, of course, assess how well these simulations encompass our data set as a function of a number of parameters. These are just some of them, like redshift, color, stretch, SNR, and so on. There is certainly room for improvement. What we do is there's a number of knobs in the simulations that we turn, and for each one of those knobs that we turn, we assign some uncertainty to how much we think we need to turn that knob. and then we propagate that through to the systematics covariance matrix. I'm going to talk about that in a second. At the end of the day, we get these large simulations of a roughly million supernovae in each simulation, and we're able to compute and predict the biases that we would observe in our survey. We compute those biases in 5 dimensions. As I said, color, stretch, redshift, and then 2 nuisance parameters, alpha and beta, that relate the correlation between the correlations that we use to standardize the Type Ia supernovae. And so here what I'm showing is just an example. Before I showed a Malmquist bias correction in 1D. Now this is a projection in 1D, but this is accounting for the differences in 5 dimensions. And so you can see here bluer supernovae don't have as large of a Malmquist bias effect as the red supernovae, because the red supernovae tend to be fainter, and so those are the ones that get affected by the Poisson noise more. So when you computed your 5D corrections, then you can make your bias-corrected Hubble diagram. So this is one of the main money plots of our cosmological result, from which we actually fit the cosmological models. So I'm sorry for the color change here. I need to change the colors. This is the low redshift sample, and this is the high redshift sample, and these are 2 cosmological models. And as you can see here, measuring acceleration is quote-unquote easy now. The question is, can we measure W to within 5%, or in the next decade to within 2%? That's the hard part. And so that's why we have 9 papers. These are sort of setting up the story for LSST and for our future analyses using the full 2500 supernovae. So we have these 2 DES collaboration et al. Papers. Those have the results in them. This one is just DES supernovae, and this one is DES combined with the other DES probes, DES supernovae combined with the other probes. We have a measurement of H0. We have the overview of the analysis, systematics, and validation. We have the photometric pipeline, a description of the spectroscopic follow-up program, a description of our simulations, a description of chromatic corrections that we apply to the supernova fluxes, and then an in-progress Bayesian hierarchical method. I wish I could get to that today, but I can't. This is not meant for you to actually read, but it's meant for you to hopefully trust that we know what we're doing. And if you don't trust us, go to the paper and read it. But the systematics fall in 4 main categories. Photometric uncertainties and calibration associated with computing the distances coming from 20 low redshift survey bands, the calibration of those bands, and then the 4 DES survey bands. They also come from astrophysical modeling, like the physics of the Type Ia supernovae. They come from modeling of the survey itself, those knobs that we're turning in our simulations, and then the redshifts themselves. These total 74 sources of systematic uncertainty. So historically, and I'm going to touch upon it, calibration has been thought of as the largest systematic uncertainty. Every image needs to be internally calibrated, and every supernova sample needs to be calibrated to every other supernova sample. So what we do is, to calibrate our images, we look at a set of tertiary standard stars. These tertiary standards are tied to primary Hubble Space Telescope standard stars. This one's called C26202. And so the low redshift sample ties themselves to that. And then the DES sample ties itself to that. And then we happen to have, by design, we have overlap with pan-stars. And so from this overlap, we can then compare the goodness of our calibration based on the overlapping images of pan-stars and DES in the overlapping stars. And we find that in each of we have 8 overlapping fields between pan-stars and DES, shown in the green dots. And we take the means of those fields, and we compare to the expected brightnesses of those stars between DES and pan-stars. And we find an overall 0.6%, 6 millimag uncertainty associated with this calibration. In red here, I've shown the prediction that pan-stars makes for us. So we make a prediction for them. It comes from the mean of the green points, and then they make a prediction from us, comes from the red line. And so what we do is, in order to propagate the systematic uncertainty associated with this calibration, we take our calibration, which is defined to be 0, and in our nominal stat-only analysis, and then we shift it to the red line. And the red line we call our systematic uncertainty, and we rederive distances. So this delta distance is relative to the stat-only case, our calibration, but then we plug in Pan-STARRS calibration, recompute distances, and then we get a distance as a function of redshift in terms of delta distance. And then those delta distances are propagated into a covariance matrix, a 20 by 20 systematics covariance matrix as a function of redshift, which we can then, we do small perturbations, and then we scale those perturbations by sigma k. And so this is done for 20 redshift bins for 74 systematics, and that's our covariance matrix. And so this is just sort of what these look like in general. This is not all of them, but it's an idea. This is a bunch of calibration, including the light curve fitter calibration, which you can see is one of the big ones. The light curve modeling, extinction, peculiar velocities, and so on. And then we take that covariance matrix and plug it into our likelihood, and we plug it into Cosmo MC, and we combine with Planck, and then we get results. But as I said, we did things blinded. And how did we know that we were going to be okay to unblind? So I'm just going to talk briefly about what we did to validate our pipelines. And what we did was we wanted to take this further than any survey had gone before. And what we essentially did was a preliminary LSST analysis on 10,000 fake supernovae. So we simulated 10,000 supernovae, put them into our images, into the real images. We discovered them with difference imaging. We applied our scene modeling pipeline. We simulated and accounted for biases, and then we did our cosmological analysis. And so you can see here the 6,000 that made it past the quality cuts, and then the residuals to the cosmology, and the best fit cosmology is consistent with the input cosmology of lambda CDM. And then we did another set of validations to validate the cosmological analysis part itself and the accounting for systematic uncertainties. So just jumping in, we produce simulated catalogs. This time it's not in the images themselves. And those catalogs, we generate those catalogs, we generate them with input sources of systematic uncertainty. Yes?
Just one question. So in the previous slide, you showed very, very nicely how you simulated everything, you got the correct cosmology out. How many iterations did it take you? Like, when you tried it the first time, did you get the right cosmology, or did you find a lot of bounds?
That's a good question. I think when we finally made this plot, we were fairly confident that we would get the right answer because there were a number of steps in the way that I didn't show you. For example, this plot here gives us a lot of confidence. And so this was an intermediary step to that validation that I just showed. So now the question is, are we accounting for the biases in the survey? And we have a number of comparisons to the real data set. And so at that point, we were fairly confident. And I think we did get it maybe on the first or second try. Yeah. Yeah.
Can I ask?
Yeah.
Sorry.
Yeah.
Really brief question.
Sure.
When you do your bias correction, right? How much model dependence can there be in this bias correction? Because you have to assume something for the model of your supernova, right? You have to do some assumption on how it's exploding in different redshifts.
That's right. Yeah, we have a source model. It's an SED model, spectral information. We have knobs to turn on how confident we are in that model, and we turn those knobs. And then we also have knobs to turn on the intrinsic variations. Those turn out to be important. But essentially, the uncertainty that we have in the model itself is propagated through, we simulate with different models, different sizes of intrinsic variation, and different spectral features of intrinsic variation, and then propagate those through the covariance matrix. Yeah.
Since you asked about this, I was wondering, so regarding mouthpiece bias,
Yeah.
You said that you modeled the bias based on several parameters. One of them was the redshift. mouthpiece bias, its relation with redshift wouldn't depend on the cosmological model.
That's right. I'm going to talk about that. Yeah. We account for that. We simulate in a number. Yeah. Any other questions? Okay. So I was saying these catalog simulations, we jump in after all the images, after the pipelines that look at the images, we just jump in at catalog simulations. And we simulate samples of the DES sample with a number of input sources of systematic uncertainty and see how well our covariance matrix and our cosmological analysis accounts for those. So what this is 400 simulations with input sources of systematic uncertainty. In this case, it's calibration uncertainty. And in each realization, we perturb our calibration by some amount. And then we analyze it as if we just did a statistical only analysis, and we look at the best fit values, the red X's. And then we take the average, so we analyze then again with our full covariance matrix accounting for these systematics. And we take the average output chains and compare to the distribution of the statistical only best fits. And we find that it is unbiased and that the uncertainties are relatively good. How good are the uncertainties? Well, that's exactly how we knew we were ready to unblind. So we looked for bias and found no bias, and then we looked at our uncertainties, and our goal was to have the uncertainties roughly correct within 20%, and we were correct within 8%. Yeah?
These DES like simulations, you have the same number, 200?
Yes. Mm-hmm. Okay, so then let's jump into the results. Any questions? Okay. So I'm going to talk about one thing. Before we look at dark energy, there's this nitty-gritty part of supernova cosmology, which is everybody's looking for correlations between supernova intrinsic luminosity and other parameters. And the question is, a number of analyses have found correlations between the intrinsic luminosity and host galaxy stellar mass. We describe this as a step function in the residuals to the Hubble diagram. And a number of analyses, like the joint light curve analysis, Hicken, Sullivan, Lampedal, have found this to varying degrees and varying significances. And if you could squint here, you can see it. But what's interesting is we did not see this in our data set. We find a value that is consistent with 0. We do look at correlations between the stellar mass and the other observables, color and stretch, and we do see correlations. This is similar in correlations to those seen by the previous analyses, but they're actually stronger, which is a bit perplexing why they would be stronger. But the fact that they're stronger gives us confidence that maybe that's why it's not there, but I'm not going to jump to conclusions. What we do is a number of tests to our analysis to see why it might have disappeared, and we find that, for example, if we change the mass fitting method, we get the same result consistent with 0. Yeah. Yeah. So that we don't decide where the step is because we don't see one, but the other ones, yes, they fit. They allow it to move. Some analyses allow it to move, and some analyses fix it based on previous. Yeah. But I agree, it's a little scary looking. Okay, so that's a bit odd, and then we looked further, and we found this other relation, which is that we found that there is some kind of correlation between the size of this mass step and intrinsic scatter. So what this is the uncertainty on the distance, and it's a bunch of things coming from the light curve fits and the uncertainty in various parameters like peculiar velocity, redshift, lensing, and then this intrinsic scatter term is this last term. It's sort of the nitty-gritty of supernova cosmology, because really all it is a term that brings the chi-squared to 1. Because, really it is, because the distribution of the supernova about the best fit cosmology is larger than the measurement uncertainties. So that's sigma int, the intrinsic scatter. And what we find is that the host mass step, which DES finds as consistent with 0, seems to be related in some way to the intrinsic scatter of supernovae. So DES finds the lowest value of intrinsic scatter of any supernova survey to date, which is in itself very interesting. And it's something that we actually have to account for because previous analyses have assumed that you could model this all with one parameter. But this clearly, we've combined with our DES sample with a LOSI sample. Those are in tension. But this is pan-stars, this is SNLS, SDSS, and then a brand new data point that came out a couple weeks ago, pan-stars plus foundation. So this is also slightly weird and we don't understand it, but it's an interesting clue to why we might see no mass step. So now for dark energy. So we combine our data set in green with statistical uncertainties in dotted line and systematic uncertainties in the shaded region with Planck 2015, and we get a W of minus 0.978, consistent with -1. And interestingly, we find that the uncertainty on the equation of state of dark energy is roughly equally contributed by statistical uncertainties and systematic uncertainties. So with 300 supernovae, we're already kind of pushing it. But all hope is not lost because with more statistics, we can learn more about the populations, about the model, the underlying light curve modeling, and so on. So here is our result for time redshift varying equation of state. This is W naught WA. In purple is the DES plus CMB result, and in green is Pantheon for comparison. So Pantheon uses 1,000 supernovae, we use 300, and so we're pretty proud of how competitive we are just already. And we find WA consistent with 0. So bringing us back to the systematics discussion, we're equally contributed by statistical and systematic uncertainties, and we do some grouping, some funny grouping of the uncertainties. We group photometry and calibration, the uncertainty due to the knobs that we're turning in terms of computing the distance bias corrections for the survey itself, uncertainty due to the light curve modeling and astrophysical modeling, and we find that they're all roughly equal, which is sort of a departure from the way that supernova analyses have thought in the past. And so this is encouraging in a lot of ways because this number here is not that large for the DES calibration. So that means we've done good work on really pinning down our calibration. But it means that there's a lot of work to do. We also investigated a number of unforeseen systematic uncertainties, as I mentioned. For example, the low redshift sample that we used has a small handful of supernovae that are 3 sigma, 4 sigma from the best fit model. And so the question is, where do you cut those? And we added an extra systematic for where we're cutting. We added, as I said, the values of the intrinsic scatter for the low redshift sample and the DES sample are not their intention. So we actually allowed to have 2 parameters. And that changes the weighting of the supernova samples themselves, and that changes cosmological fits. We added, as I said, a number of systematics associated with simulating your bias correction sample in different cosmologies than the best fit cosmology. And then we added a small redshift systematic, could be potentially due to a cosmic void or whatever your favorite reason is that we might have this tiny redshift systematic that is very hard to tell if we actually are measuring to this accuracy. If you total all these up, they total roughly 2% in equation of state, which is, as you saw on the previous slide, of similar size to the other major systematic uncertainties. So we sort of added this new grouping of things that we need to focus on. Of course, you can always add more things, but we thought these were essential. And the single largest systematic in our analysis is this low redshift outlier cut, which I'm going to talk about in a second, is hopefully going to be ameliorated. So just quickly comparing our results to recent results, with the caveat being that for each of these analyses, JLA, PanSTARRS, Pantheon, DES, I've listed the samples that were used, the data samples that were used, and you'll notice they're not all independent. So these are not independent measurements. Well, these, so if you focus on these two, I included here DES only. So that's not including the low redshift sample. You'll see the error bars are bigger because we don't have that constraint on the cosmological model. But you could, in theory, compare this result to this result with the caveat that we use pan-stars to evaluate the goodness of our calibration. One other cool result that popped out of this was combining with the other DES probes, so weak lensing and BAO. And we like to say that this was a APJ letter, but what it is essentially the first single photometric probe to by itself independently rule out a no dark energy universe. So we're not combining with any other data sets, just DES supernovae, 3x2 point, and BAO. We get a W of -0.8 plus or minus 10%. And this is the plot here if you focus on the gray shaded region. When you add other external samples like low Z or Planck, then it goes down to this. And for comparison, if we just took the DES supernovae and added Planck, we get this result. And so if you just look at the uncertainties, you can say, hey, look how awesome DES is. You know, we're doing together almost as good as Planck. And the last piece of results I just want to touch upon is our H0 measurement. We implemented the inverse distance ladder H0 technique. That is a technique that uses BAO measurements. In this case, we use SDS-BOSS and 6DF BAO measurements shown in the white data points to break the degeneracy between Type Ia supernovae and H0. The Type Ia supernova intrinsic luminosities we marginalize over, and so that's effectively marginalizing over H0 unless you break that degeneracy with some other distance scale. So we use, we take the DES supernovae in the black points and sort of stick them on the BAO points here. And then if you follow this curve back, essentially at redshift 0, this is H0. And we assume a minimal cosmological model that's a polynomial model. We assume a Gaussian prior on the sound horizon coming from Planck, caveat. And we get H0 of 68. We wanted to take it as because that is essentially been done with a different data set. So what we did was we took that technique of propagating systematics and propagated it through to H0. And so this is for a number of different sources of systematic uncertainty, and we get a budget. This is the first ever H0 inverse distance ladder budget. So interestingly, it's not quite as limited by systematic uncertainties. So those are the results. If you want to play around with stuff, it's all there. Or going to be there today. I got a little busy making these slides. The transmission curves, redshifts, photometry, light curve fit parameters, distances, simulations, bias corrections, binned Hubble diagram, covariance matrix, anything you could want to jump in at any point in our analysis, you can go for it. And just a quick couple notes about the future. So some of the challenges that are coming up for our future photometrically classified analysis are, of course, the photometric classification itself, but I hopefully want to change your way of thinking about this because most people think, oh, the photometric analysis, you really got to worry about photometric classification. That's going to be your biggest systematic. And I would argue that a lot of work has been done on this, including by the LSST desk team, and they're really doing a good job of it. And I don't think it's going to be our largest systematic, and I'll show you. Here's that systematic discussion, the groupings here. And then the question is, what is going to be the systematic associated with the contamination due to core collapse supernovae? And a recent paper by Jones et al. That did an analysis with pan-star supernovae found this to be around 1% in W. So currently, this would not be our largest systematic. In addition, we have promising work on the classification itself. We use random forest machine learning to do photometric classification, and it does a really good job on simulations. This is efficiency and purity, your typical ROC curve. And we find that you can get roughly 98% purity with 90% efficiency, which is really promising. And then, of course, I don't trust anything until it's been put on real data. And so this is the 3-year spectroscopic sample, and it only had 1 false positive. So that's promising. Another thing that we have to think about is this low Z anchor. That data set is antiquated, and we are currently not very well able to model it for a number of reasons. One of the reasons is that the current data set is not from a rolling survey. Here, for example, is the median color of supernovae in that sample versus median stretch. You can see DES, pan-stars, SDSS, and SNLS, and then all the way over here is the low Z sample. So the question is, is this a selection effect, or is it the supernova population at low redshift? And how do we account for that? We don't have a good way of modeling the low Z sample currently because it's not a rolling survey, so we can't easily simulate a rolling survey, a non-rolling survey. And so thankfully, in the last month, the Foundation data release has just come out, and it found this. So that's a good sign for our ability to model low redshift supernovae. The Foundation survey is a rolling, it's based on a rolling survey. So it's a low redshift survey that listens to a bunch of other rolling telescopes and alerts and points to things once they're found. And then the last thing I just want to touch upon is a host galaxy confusion discussion. When you are doing a photometric analysis, photometric classification, you need, and you want a redshift of the host to determine the redshift on your Hubble diagram, you need to assign that supernova with a host. So there's going to be, especially at high redshift, some probability that you're going to assign it to the wrong host. And so there's been a study by Ravi Gupta, and we're going to improve on that, hopefully, because he, with his host assigning algorithm, found roughly 20% misclassification from simulations. And so the question is, can we improve upon that algorithm? Or no matter what, we're going to have to model this misclassification, this misidentification of host galaxies. And so, of course, there's a lot of work to do, but this is just a quick forecast of what we think we might be able to accomplish, conservative forecast. Of course, not assuming any improvements in systematic uncertainties. This is evolution of dark energy, and in the blue dotted line is this 2500 supernova sample that we think we have sitting waiting for us to analyze. And that's just about it. Any questions? Thanks.
Hi, do we have any questions? More questions, I mean?
Yeah.
So, a couple questions. So,
Yes.
So, question is, do you plan to have a combined catalog with the DES supernovae together with the Pantheon supernovae? Because then you have to refit all the systematics all together.
Oh,
right?
yeah. If we don't do it, someone else will. But it's not easy. So fortunately, we have a lot of the structure to do it relatively quickly. The question is, do we prioritize that over, with the relatively limited manpower, over the photometric sample that we have right now? So we want to do it. Yeah.
And the second question is, when you're talking about using the spectroscopic supernovae, you say you can achieve, if I understand correctly, 98% purity with 90% completeness. Is that published result, or is that internal
preliminary,
result?
Yeah. It's not published.
And are you confident on this number? Because this seems like very high numbers.
When I see those numbers, I am very skeptical, but when I saw it on the spectroscopic data set, I was given a little bit of push in the right direction. So
yeah,
that's not my work personally, but yes, it's not published yet either.
Yeah, okay, but I guess it must depend a little bit on how you model your core collapse, right? So how do you trust this model?
Yep. That's a large area where we are going to be doing the improvement, hopefully with combining with the Pantheon sample of spectroscopically classified supernovae. It also has been published an entire set of core collapse supernovae. In addition, not just modeling the core collapse distributions that we include in the training of our models, but finding a way to model the types of supernovae that make it in may not be the same distribution that you started with, and where they end up on the Hubble diagram, hopefully they're, you know, where that's all has to be modeled. That's where we have a, yeah.
So I have a question about the covariance matrix, of course.
Okay.
So a couple of questions. What's the dimension of the covariance matrix? How is the covariance matrix estimated? What's the dimension of the covariance matrix?
It's 20 by 20 in redshift bins, and each entry is a uncertainty in distance.
And how was it estimated with the simulations?
Yep. From a combination of simulations and from changes to our data sets. So what we do is we estimate distances using a nominal assumption of our analysis. Then for each systematic, we change that assumption, whether it's in the light curve fitting process itself or whether it's in how we computed the bias corrections. We get a new set of distances, and that gives us a delta distance that we plug into the covariance matrix for each redshift bin.
Okay. And how many nuisance parameters did you have to marginalize over?
4, 5. Yeah. Yeah.
So the inverse ladder you showed, it didn't use CMB information.
It used CMB information to constrain the sound horizon.
Ah, okay.
Yeah.
And another question, I think the expectation was to find more supernova than DS actually found in the end.
That may be, but I was in high school when those expectations were.
But do you know, like, if there is an explanation for why?
I think some people might know. I don't know the answer to that. No. We're working on a study of the overall supernova rate. So think of supernova cosmology as a study of the cosmology or as a study of the Type Ia rate. That's one of the projects. So I'm not sure rate has. I don't know if that's come to fruition.
Very quickly, you showed random forest results for the photometric classification. You said there was one false positive.
Yeah.
How do you know?
So that data set was so for the first 3 years of DES, we followed up a number of supernovae that we thought were 1As, and with spectra, and a number of them were not. And so we ran the photometric classifier on that full data set. Roughly 100 of them were not type 1As from spectral classification, and we ran a photometric classifier on those, and only one passed through.
So you decided who to classify before? You
spectroscopically classify, yes.
So you decided, but you trained on what?
We trained on the full distribution that we believe encompasses type 1A, encompasses all supernovae.
But for which you have spectra and you know.
Yes. And that's one of the difficulties is this spectral data set that we train on encompassing the full distribution, yeah. You want to yell it?
Looking forward to LSST analysis. Which of these systematics are you the most worried about? And which ones will not be an issue?
Probably should have figured that was going to be asked. Are we most worried about? I'm most worried about currently the confidence that we have in the light curve modeling. So I believe that the intrinsic scatter term comes from the fact that we're underestimating how well we know the light curve model. We account for that downstream, but that adds a systematic. We need to account for it further upstream in the modeling itself, which will not come from improvements probably from LSST. It'll come from spectra.
But does that require a new analysis framework, or can that fit in?
So yes, we're working, not myself, there's a team of people working on a new light curve analysis framework called SNEMO. It's based on SN factory data, and they claim to have somewhat resolved this, but we'll see how well we can actually implement it.
Thank you.
Yeah.
Do it.
Yeah.
So I'm a bit surprised also by this reduction in the intrinsic scatter of the supernovae, right? 0.06, 0.07 was previously only thought to be possible in the infrared.
Yeah.
So how do you account for that? I mean, you mentioned briefly,
it's possible.
The extra variance, is it because you did some better modeling of some other correlations?
I wish I could say that. I don't know the answer. It could be from the fact that we're going to higher redshift, and so we get more infrared information. Closer to the infrared.
It's not much higher than JLA, I guess.
That's right, because of SNLS, and so that's the one exception to that rule. That what I'm trying to say, but I don't know exactly. Maybe something could have entered into SNLS at some point that added some intrinsic scatter that we've somehow accounted for. But I don't know if I shouldn't say that because I don't know if that's the truth. We like to pump our chest about that value, but we don't have a good answer for why it is so low. And so we have to account for it as a systematic. If we knew why, then we could get rid of the systematic, and that'd be great. We lose a lot of the advantage of finding this low value because we have to include a systematic that doesn't agree with the other supernova samples.
More questions, comments? Well, if not, we can thank the speaker again.
Thanks.
And now we go to the next speaker. Who's that? Ah, here.
Is this the one?
Yes. I think this is because we're using
Okay, yes. Let me get my adapter, hold on.
Mm-hmm.
Oops, that's not my presentation.
It's just a picture of Sao Paulo. This is it. Okay.
Okay, can people hear me?
Okay, let's go. And we have now Nikolas Kokron, right? So we talk about sharpening cosmological constraints with EFT methods.
Yeah. Okay, so hi everyone. I'm Nick Kokron. I'm a grad student at Stanford. I actually did my undergrad here in Brazil. Rogério was my advisor, so it's always good to be back. Today I'm going to be telling you all about something that I was working on during my first year there at Stanford. And this is work that has been carried out for a long time and with a lot of different people. So I think it's fair to acknowledge all of their effort. Our main collaborators are Jérôme Glazès, Pierre Zhang, who's a PhD student in China, Leonardo Senatore, who's been kind of leading this project, and then Dita Markovic, Florian Beutler, and Hector Gilmarin, who have been helping us with the simulation and validation side of this project. So I'm going to be talking about these EFT methods, which I will define in a bit. Just keep this picture of the Matryoshka doll in mind, because I feel like it kind of encapsulates the physics of these EFT methods. There's a review written by Rafael Porto, who was faculty here, and he actually opens with a similar picture. So I think it's kind of a cute representation of what we're going to be doing. So without further ado, you're probably asking, man, he started this talk with an acronym. What's EFT? Well, EFT is something called effective field theory. This is a general paradigm which kind of exists in all fields of physics, and it's basically valid when there's a hierarchy between length scales in the system that you're studying. It's incredibly successful. The standard model is an example of an effective field theory, condensed matter systems, statistical mechanics, biophysics, gravitational waves, inflation, hydrodynamics. All of these have used EFTs to a lot of success. And actually, around 8 years ago, a paper came out by a group of people which proposed using these techniques to study dark matter as a cosmological fluid. And basically, the length scale hierarchy here is that the distribution of large-scale structure in the universe, for example, shouldn't depend on the microphysics of star formation going on in some small region. So there's a hierarchy between scales there. And what's good about these methods is that they allow us to import particle theory technology into the prediction of cosmological observables. So what these EFT techniques do is that they provide an analytic, physically well-motivated approach to computing quasi-linear corrections to cosmological observers. This is a lot of words, but basically this is a good thing. Because we kind of always want to push into these more nonlinear scales as better surveys come online. And so people who are kind of more in tune with cosmological perturbation theory might be asking themselves, wait, doesn't standard perturbation theory or SPT do this already, and hasn't it been doing this for a while? Yes and no. SPT is kind of the most famous example of all of these perturbation theory methods. They all have the same objective, which is to compute these observables at smaller scales to high precision, but they all have several pitfalls. So for example, SPT actually gives formally infinite answers already for your first correction. The fact that it doesn't for our universe is just kind of a lucky thing. And so, for example, if you actually look at the nonlinear power spectrum and how these corrections with SPT scale, you see that at one loop you kind of overshoot how large your power spectrum should be. 2 loops you undershoot it. It doesn't actually ever converge. This picture I took from a talk given by Tobias Baldauf called Practical Aspects of the EFT of LSS, which is a really good talk if you want to get into this field. And so basically EFT is an extension of SPT, and it uses these tools of particle theory to control for these weird infinities which we see popping up. You get a bunch of stuff for free with it. So you get basically tracer bias from gravitational physics, you get sort of stochastic biases, so these two things Marco talked about this morning, and I'll touch on them again. You can get predictions for higher order redshift space distortions. You can get calculations for these IR resummations, which are useful if you want to do BAO physics. You can get baryons and a bunch of other things. So I'm just very quickly try to explain to you what are the physics behind these corrections. So if you've done sort of linear perturbation theory before, then you remember that you take the first and the second moments of the collisionless Boltzmann equation, along with Poisson's equation, and you kind of solve them sequentially. So you have Poisson equation, you have the continuity equation, which is the first moment, and you have the Euler equation, which is the second moment. Well, zeroth and first, actually. And basically what we do is that there's this stress energy tensor which pops up, and we set it to 0 in standard perturbation theory. But the statement of EFT is that this stress tensor is actually not 0. And you can actually write it out in terms of quantities that you kind of know how to compute already, like your density and your velocity and derivatives of them. And basically they just have to respect the symmetries of your theory, which here are Galilean invariance, because this is a Newtonian theory, and rotational symmetry. And kind of the beauty of it is that higher order contributions are always smaller because of the scale hierarchy. So like a Matryoshka doll, the things that come out are always smaller. So explicitly what we get is you can write out the stress energy tensor. This is kind of the first few relevant terms that you get. And so you get something that looks like a sound speed correction of this fluid, which is to its density. You get something that looks like a bulk viscosity. And you get something that looks like a shear viscosity. So these will alter your equations of motion, but you can still solve them in the same way that you would do in standard perturbation theory. And you actually get that these 3 parameters enter in the power spectrum as 1 parameter. And this is what the correction looks like. And it turns out that when you do this, the quality of fit for the power spectrum improves dramatically. So this is a 1 parameter fit, and you actually see that you're within a 3% up to a K of 0.6, which is pretty good. These oscillations that you see here are because when this paper was written, this IR resummation hadn't been invented yet, but nowadays it's implemented and this makes this a straight line. And so that's one of the parameters that we get, but this is really only describing dark matter. So unlike some US news agencies, the universe isn't fair and balanced. You need some sort of theory of biasing. So everything that I've talked about only works for the dark matter density, but really we observe galaxies in these surveys which trace dark matter halos, and the dark matter halos themselves are actually biased tracers of this smooth continuous density. So this is a picture which has actually already been shown today, but you have to develop some sort of description to relate this distribution of density to these collapsed objects that you see. And it turns out that these EFT principles actually guide you and tell you how to describe this procedure. There's a lot of work that has been done in this. This review, which has Marco also mentioned, I think is the most comprehensive one. But basically you get two sorts of contributions. You get these first ones, so these are all of the bias contributions that you get up to third order, which are deterministic and just kind of come from gravitational physics. And then you get other contributions which come from, which are called these stochastic bias contributions, which come from the fact that you look at a random realization of a tracing of this field. There's something else that we need to include in the modeling, which is redshift space distortions. And this is because we don't actually observe the radial position of a galaxy, we observe it in redshift space. So there's a coordinate mapping that shows up where now every time that you have a position, you're actually mixing the velocity field in. If you use this coordinate mapping to relate the density field in redshift space to the one in real space, you get kind of this ugly expression. And then you can Taylor expand this exponential, and since we're working at what we call one loop order, this is everything that is cubic in density or velocity, you get this expression. This had already been worked out before, but it turns out that these kind of squares of velocities, velocity times densities, and cubes of velocities being integrated over all momenta diverge. And so you need to add more of these counter terms that I mentioned, like the one for the density itself. And so these are what the directions look like, and if you just count a bit, you see that there's 1, 2, 3 coefficients that end up showing up. So if you jump forward in time, about 4 years since the first few of these papers were written, and about 30 papers, in 2016, they end with long wavelength statistics that are routinely observed in LSS surveys can finally be computed in the EFT of LSS. This formalism, thus, is ready to start to be compared directly to observational data. This was 2016, so you have to jump forward about 2 years and 10 more papers. And I think that now we are actually in this position. So I'm going to talk a little bit about the analysis that we set up and we've been using. So with kind of all of these tools that I outlined above, so this density correction, the biasing, the redshift space distortions, the IR resummation, you can write down a model for what the anisotropic galaxy power spectrum will look like. And it kind of looks like this. And so these functions Z are redshift space perturbation theory kernels. You get terms which are related to the redshift space distortions. You get the stochastic terms. When I was little, I used to watch this show called Sesame Street, and in it they had a character called The Count, and he taught you how to count. So if you go through this exercise here, it turns out that there's 1 bias parameter here, 2 bias parameters here, 1 here, and then a total of 6, and 1 for the bispectrum analysis, and you find 11 free parameters in this model. Actually, if you naively look at these kernels, you will find 12 bias parameters alone, but you can rewrite them in a basis of less degenerate configurations and bring this down to 4 free parameters. So we have a model with 11 free parameters that we can use to describe survey data, but we also need more of a statistical framework for this. So this is something called working with the window function and with the likelihood. Yeah? Not in this analysis, no. But in principle, it's another free parameter. Only one? Depends to how small you want to push the scales. Basically, the baryons are kind of degenerate with this correction over here. It's also like a k² over k nonlinear. So in a sense, they are being included. But if you have a 2-fluid description, you can get counter terms for the baryons explicitly. We can talk more about this offline. So one thing that you have to do for these 3D surveys is apply something called a window function. And the way that this has been done historically is that you would just take your power spectrum, Fourier transform it into a correlation function, multiply it by this window function, and then Fourier transform back. But kind of by construction, these EFT predictions start diverging as you go to small scales because they're accurate until kind of the regime where the theory is expected to converge. But if you're doing Fourier transforms with diverging functions, you're going to have a really bad time. So we had to think of another way to apply these window functions. And I worked a lot with these pseudo-CL estimators when I was an undergraduate. And it turned out that if you can use these window functions in a similar way and write pseudo multipoles. And this applies the window function directly in Fourier space. You don't have to do FFTs. This actually speeds up the chains a lot. And then if you were very observant, 6 of the 10 bias parameters that I wrote down actually only enter linearly in the prediction of the model. So they factor quadratically in the likelihood, and this means that we can use Gaussian integrals to analytically marginalize them out. So it turns out that this model that originally had 11 free parameters only ends up having 3 cosmological parameters and 3 bias parameters being varied. And the ones that you're analytically marginalizing out, you can actually have strong physical priors put on them. And so you don't degrade your constraints, and your chains are just a lot less painful to run. So the next thing that we did after writing down this model and going through this likelihood and window function discussion is that we started looking at a big set of different numerical simulation suites. You can ask me for a list later, and I can tell you what they all are. But what I'm going to be talking about today, or right now, is something that are called the lettered challenge boxes from a paper by Nick Hand and Urosh. The model that they use in this paper has 13 free parameters. But basically, these are very high resolution boxes with varying HODs, central galaxies, satellite galaxies for each of these catalogs, and covariance galaxies that are scaled to the volume of the BOSS DR12 release. And what we find for constraints are, as we vary our Kmax, basically you find constraints that are on the order of 0.01 for omega matter, for example. Reference Planck 2013 had a constraint of around 0.014 for omega matter, so we are actually kind of competitive with Planck just from pushing these small scales with this modeling. And all of those terms that we add scale differently on cosmology, so this helps with degeneracy breaking. What I think is slightly more interesting to look at are maybe the contour plots. So the posteriors that we got for the cosmology, so these are for 4 different boxes that were available here. You can see that we are kind of always within the best fit for the 3 cosmology parameters. If you actually look at the product of the posteriors, so if you had like a way larger survey, we find some slight biases in AS and H on the order of half a sigma. What I think is pretty neat about this plot is that you can actually pick out exactly the different HODs, like the model picks out the different HODs of each of these boxes, but the cosmology subtriangles are all kind of on top of each other. And we also found this interesting tight relation between 2 of our bias parameters, which is related to how they renormalize each other. So this is like some interesting renormalization physics that was popping up here. So I mentioned that we could also get the bispectrum, so we turned to another suite of simulations, which are the Pachy-Mox that were used in this BOSS DR12 analysis. And we also find kind of similar results in terms of the sizes of our error bars. But for the Pachy simulations, since these aren't as good, as we push to smaller scales, the chains start going crazy because the simulations actually aren't really modeled up to those regimes. So we can also self-consistently include bispectrum predictions. So this chain shows one just pure power spectrum chain, and then as we increase the sizes of the triangles that we're taking into account. And you see that the cosmology actually doesn't get much better here, but we do get much tighter constraints on these different bias parameters. And we were a bit perplexed by this, since you would expect at least some sort of maybe breaking of degeneracies between AS and B1. But we were talking to Albert, who's one of the postdocs there at Stanford, and these Pachy simulations don't actually have really faithful bispectra, and especially not to Kmax of like 0.1 for triangles. So maybe this is just an artifact of the simulations, and if we had better simulations, we would be able to test this more deeply. Another test that we wanted to do is kind of a test of how fundamentally biased is this theory model that we were writing down. And so a way to do this is to kind of try to combine it with a light CMB prior, which is the sound horizon at decoupling. Basically, this imposes very strong constraints on where you should be in the H omega matter plane. And when we apply this, we don't like the best fits aren't very significantly shifted away from their true values. And if the model, if the EFT model were fundamentally wrong, you would expect to go to the wrong best fit. So this is also a reassuring for us. So we looked at a lot of different simulation suites. We were kind of confident in our results, and they looked pretty cool. So we went back to BOS DR12, just the public release, and ran an analysis. So like I mentioned, the simulated constraints were already pretty exciting, at least for omega matter. You're kind of at the regime where Planck was, with simulations that were built in 2015, or where Planck 2013 was. And what I can say is that the error bars in the data that we have found are comparable to the simulated chains that I've shown, but we're not actually done running them yet, and we're kind of making sure everything is okay. But hopefully before Christmas, we'll be tuned and you can actually glimpse what our final error bars are. So now there's an aside, this is a school on LSST, so I think that I should comment a bit on the relevance of this. Working in this project, so I come from survey cosmology, and I realized that there are kind of barriers between this community and the other survey cosmologists, which I won't comment on camera. And sociology aside, I think these techniques are actually really valuable for DES and for DESI and for LSST. Please don't shoot me for saying this, I'm just the messenger. But we now have these pretty fast codes and analysis pipelines set up to do this for spectroscopic surveys. I don't think extending this to photometric observables like power spectra and shear and galaxy lensing is too difficult. And for really interesting because you don't have these bias parameters and you don't have these redshift space distortion parameters. So you can actually push the modeling much harder for lensing without needing any free parameters. So kind of wrapping up, we've done extensive tests of this EFT modeling technique for the anisotropic power spectrum. Looks like we can wring out even more constraining power from existing data. I think combining these techniques with survey data in the future is a really tantalizing prospect, but maybe given Marco's great talk this morning, we should just abandon everything and go to the field level. And I'll just leave you with this very outdated chain that we ran on data, where these error bars are Planck 2013, and before we change the modeling to make it more accurate. And this maybe already gives you a sense of what we find. And that's it. Thank you for your time.
Thank you so much. Do you have questions?
Sure.
Is that the shade written, the purple one is in AS and H are finding pretty inconsistent results with Planck?
Yes. Well, so for AS, it's very hard for a large-scale structure survey to actually measure it because of all of these bias degeneracies. I fought very hard for us to show sigma 8 here, but I was shot down by collaborators. So I agree. When we include CMB data, this kind of shifts to be more with where you'd expect. Not even for the full CMB data, just this distance prior. And with H, I mean, we're not super in tension with Planck, and we kind of are finding values closer to the W map, no? Slightly higher H's. So.
True. I mean, AS is more difficult to measure, but I would expect to see a larger error bar, not the shift. But we can discuss this offline.
A larger error bar
for AS, but you're seeing a shift.
Yeah, we thought about this. I think it is because of the bias. It's kind of hard to calibrate on so if you look at the plots that we ran with simulations where we know kind of what the bias is and we know what AS is, we're never unbiased. And as soon as we ran a chain on the data, kind of AS shifted to the left. So we think this might just be some sort of systematic in the measurements themselves.
Okay.
Is it possible to translate these coefficients in those physical quantities, sound speed, viscosity, shear, and bulk viscosity.
Yes.
And the scale where they start to become important.
Yeah, so the scale that they start to become important, we kind of understand. There's this parameter that I've been kind of just, this K is kind of where you expect the perturbation theory to stop breaking down. And we know roughly how to estimate it. It's related to looking at the dimensionless power spectrum and where that goes order 1. But people have, like, so in the original papers, people went to n-body simulations and actually measured what was this effective sound speed for the fluid that they were looking at, and with different techniques, and they find very consistent values for them. So there is some like physical meaning to them. It's kind of harder for the dark matter fluid case because they contribute the same way to the power spectrum, so disentangling them at the level of the power spectrum is hard, but you can build actually different estimators to tease out the individual values of these if you have the full n-body mocks.
Do we have further questions?
So you have two expansions. One is this in the electromagnetic tensor, and the other is the bias.
Mm-hmm.
Are they related?
No, in the bias expansion, the density field that is showing up is already assumed to be kind of renormalized by this energy momentum tensor expansion. You write the bias expansion for the yeah.
What is the expansion parameter?
You
can say the K over K now.
Yes.
Look at the top equation doesn't appear K over K now,
right? Right. It doesn't here. When you so the way that K over KNL shows up is that to actually get this, you have to do an explicit smoothing of these equations. And when you do this like actual smoothing and rewriting things in terms of the long wavelength operators, everything like kind of pops out with this scaling. So it's a bit more involved to show it.
There's another scale that shows up, is Km.
Right.
What is that?
So Km is a scale related to the fact that so Km is a scale that shows up explicitly for biasing, and it's related to these stochastic operators. So Km is kind of the wavelength corresponding to the mass of the tracers that you're looking at.
So it's galaxies.
Yeah, well, it's halos. It's a halo scale. But it's the scale at which, for example, you would start to expect deviations from Poissonian shot noise to show up and dominate. Not the exclusion type effects that Marco mentioned, because those affect small scales, but these affect high K.
Can you estimate those from comparing the simulation?
Yes.
KL and KM. What's the difference?
Yes. So Km depends on the sample that you're looking at, right? So this is kind of depends on I think the median mass of halos in your catalog. KNL is in principle a fundamental quantity, although it's cosmology dependent if you try to estimate it using the dimensionless power spectrum. But yeah, there have been papers by Raul Angulo, for example, where they look at these corrections and how they start mattering for example, very massive tracers much earlier than for lighter tracers. In our analysis, we actually don't find any hints well, we find very, very small hints of these KM-related parameters showing up, which are these bias parameters over here and these.
Sorry, I think that makes me
Uh-huh.
think that what's the K max that you're doing for the data?
Right, so for the data right now, we can very confidently go up to Kmax of 0.25, which is what a few of the SDSS papers actually use, but their modeling is weird if you look at it, and I can tell you why I think it's weird.
But do you have to work case? Is it okay to model the variance and something kind of case with? Do you try something?
We haven't looked at this now. I think this is a future project that group wants to do. Because it turns out that there's Yeah, I can talk to you a lot more about this online. But for the data, we tried to push to Kmax of 0.3, and the modeling looks fine, but the chains look very weird, even though the best fit models look like the quality of the fit is perfect for the points that you include, but the chains get very weird. So we're still trying to figure out what exactly is happening. The constraints get a lot wider. Like the error bars increase a lot for the measurements. Yeah, so basically if you stare at this enough, you can kind of see that we're shifting away from the best fit value as we increase Kmax, and we have some sort of criterion to determine when we're too far away. If you start pushing this back to say, so this is 0.2, 0.25, 0.3, if you go back to 0.1, then you're bang on, but like very fat.
So my question was basically already asked, but I'll just refine it a little bit just for the. So in the end of the day, if you take the ES data or LSST data, I mean, what's the Kmax that you would be confident to apply this method blindly now, as it is? I mean, 0.25, would you do 0.25 blind?
I mean, even in DES, if we're doing blind analysis, we rely a lot on our simulated catalogs, like the buzzard catalogs that Joe DeRose has been running, which were like really important for the collaboration. So blindly, I would say that it's, and I'm sure people will contest me on this, but the Kmax at which point the runs on buzzard or whatever your simulated high quality catalog is start looking terrible or very biased, you know.
So what's the Kmax? Not 0.25, then
well, it's
the current
DES is angular, right? So I'm not sure if I can. You can't. So for Y1, people used something that roughly corresponds to, well, modulo some 2-piology, like 0.125 as Kmax. Although, actually. Yeah, I had a lot of discussions with this last week, or with people last week about this. So it's either 1.25 or 2 pi times 0.125 as their Kmax. But they, in DES, specifically use kind of halo fit for all of their predictions. So I would try running things at 0.25, which for SDSS seems to work well so far, first, for these catalogs. And kind of for all of the simulated suites that we've looked at, 0.25 we've never had problems with 0.25.
Until which redshift you went?
So this sample is at redshift 0.55 that we've been looking at.
Okay.
The framework should break at some point because you're assuming fluid, right?
Yes.
So do you have in mind some way to let's say, Boltzmann equations and then apply this all again up to which scale do you expect this to work?
So I think the lore has been that this works up until where you expect to get shell crossing. There are actually papers by Zvonimir Vla and others who have kind of extended these approaches to things beyond shell crossing using Lagrangian methods. So what we do here is that we use compute everything in the Eulerian frame and then do this IR resummation. So if you're, Marco alluded to this, if you're in the Lagrangian frame, you don't have to worry about this as much.
The scale of shell crossing.
Yeah. Yeah.
You said before that you could push up to K 0.6, but that one depended on the redshift,
right.
I guess, right?
So this is an older paper by Carrasco. So this is at 2 loops. For the multi-dark simulation, they see that the fit works up to 0.6. I don't remember what the redshift of this was, actually. But it's definitely, I think it is around 0.5.
Okay. So have you tried to go up to, just for fun?
So the problem is just that a lot of so we're using public data, and we think a lot of the kind of systematics tests and, you know, like making sure the data is reasonable, like with the errors that you get and things like that. I think they only really do this up until the point where SDSS itself stopped the analysis. Okay. So you can't take their measurements. We've tried to push in simulations, but then we also run into this issue of the simulations where we have a lot of different suites. The quality at small scales isn't very good because they're not actually n-body simulations.
because both, I think, well, both goes up to 0.9, very redshifted. So, but they
Right.
goes in the analysis, they do it up to 0.35.
So it depends a lot on sample, right? Like CMAS2, I think, is 0.55. Dida Markovic had an analysis which used a sample at 0.61. So, but I think it probably, yeah, I think they have galaxies up to 0.9.
Yes, that's fine. Do we have more? Sorry, do you have more questions, comments? Yes.
Technical. In practice, how you do the balance between the bias that's coming from the deterministic part with the stochastic one?
Well, so you can. So the bias that comes from the deterministic part is folded into the perturbation theory kernels. So these are actually, they're tied to a very specific type of scale dependence, which is coming from what these kernels are doing. The stochastic parts always are kind of corrections that you get either just to the linear power spectrum, which with these redshift space distortion ones, or with things that scale like 1 over the number density of galaxies, and odd or even polynomials of that, which is kind of set by the symmetries. So the bias, the deterministic bias, is going to have a lot fancier shape dependence than the stochastic bias.
Okay. Thank you.
Okay. More? If not, we can go.
Yeah, thank you.
Again. I think now we have coffee break and poster session, I think, up here upstairs. And we meet in 30 minutes, right? Yes.
Sempre tenho dúvidas ainda quando
Eu também.
We have the microphone.
Oops.
Are you going to offend me?
No, I have a question that is a bit too technical.
Okay.
Because in some of these papers, when you do the RSD part, in some of these papers, you find that they don't want to renormalize, they don't want to